So hey guys, welcome to the channel CodeChef. If you want to learn competitive programming and get a good hold on data structures and algorithm, this is the right platform for you. Every week there are several videos on the CodeChef contest problem as well as various videos which will enhance your skill in DSA. So if you are new to the channel, then please do subscribe the channel. Myself Shirayu Jain, I'm a CodeChef educator, and in the series of dynamic programming, today we are taking coin change problem. Okay guys, so now let us try to understand the problem statement of the coin change problem. It is one of the standard problems in the dynamic programming and it has quite a variant. The problem that today we are dealing with is this. So let's start with the problem statement. So what we have been given an array which represents different coin denominations, and we have been given a total amount t. Right, so we have been given an array which represents different coin denominations. If you can see here, this is the array, and if we look at the example, how many coin denominations we have 3 coin denominations of 1, 2 and 5. What we need to do, also we have a total amount t. This is the total amount t. We need to find the minimum number of coins to make the change for t, right? So if we want to make the change for this t amount, then how many minimum number of coins are required, right? We have the denominations. From these denominations we can pick up the coins, and we need to form the change of this total amount t, right? The note is that we have the infinite supply of the coins and each coin can be used multiple times, right? So we have infinite supply of all of these denominations, and each of the denomination can be used multiple times, right? So if we look at this example, so 11, right? So if we take the denomination 1, only denomination 1, then we would require 11 coins of 1 to make 11, right? We would require 11 coins of 1 to make it 11. So this is one possible case. Now if we take the denomination 2, right? So what we can do is we can take 5 coins of 2 and 1 coin of 1 to make the sum as 11, right? So how many coins in total? That is 6 possible coins, right? So to make the total 11, we require 6 possible coins of this particular dimension. Let's come on to 5, right? So if we take 5 as the denomination, then how many coins do we require? That is 2 coins of 5 and 1 coin of 1, right? So it will make the sum 11, right? And the total number of coins are 3. Here it is 6 and here it is 11. So if you see here, we have seen 3 possible combinations from it. And what is the minimum number of coins that we require is 3, right? So that is the result. That is the result that we are looking at, right? So this is a typical problem statement, and this is a very standard problem for dynamic programming. And now let's see how we can form the approaches of this. We'll just, as usual, follow the approach, draw some observations, form the recursive approach, and then finally go through the dynamic programming iterative approach, right? So let's look at the approach. Okay guys, so now let us start with the approach. So the observations that we can draw from this particular problem is that we have 2 options, right? So whenever we are selecting a coin, what we can do is, the first thing is we can include the coin in our bag and then deduce the amount of the coin from the total amount that we have been given. That is the first option, that we are selecting the coin, right? The second option would be excluding the coin. Means that we are not taking the coin into the consideration. We are not taking the coin, right? So these are the 2 options. Whenever we are making a change of amount, then either what we can do is we can take the coin in the change for the amount. Otherwise, what we do is we do not take the coin. We take some other denomination, right? So that is the possibility that we have here as well, right? So to deduce the recursive approach, let's try to understand how we can do this. Is, let's see that we have the amount, the total amount that we have is 3, right? This is the total amount that we have. Now we want to make it to change, right? We want to make it to changes, right? For the number of denominations. So what are the denominations that we have is either 1 or 2. This is the denomination that we have. So if we want to make the change of this total amount, then how we can do this is, either what we can do, we can take the coin 1. We can take the coin 1 and reduce the amount to 2. We can take the coin 1 and reduce the amount to 2. That is one single possibility. Otherwise we do not take it. And let the amount be 3, right? This is one thing. Or what we can do is we can take the amount 2 and make it to 1. we can take the amount 2 and make it to 1, otherwise we do not take it. So at each and every case we have two things: either take this coin, otherwise don't take it; take some another coin, take this, otherwise don't take it. So if we try to take one, right, if we try to take one, then the problem is divided into sub problem, that is 2, right. We need to have the optimal answer for 2, right. So it is not the case that we have taken one, then we cannot take it again. Of course we can take it again. So what is the case? If we again take it 1, then the answer would be 1. This is again a sub problem. And if we again take 1, then the amount is 0. That is the endpoint, right. We have taken all the amount into consideration, and how many coins are required? That is 3 coins. 3 coins are required to make this amount, right. That is one possible case. Let us say that if we have reached this position, this coin into the consideration, that is 1, what else I can do? I can take 2, right. I can take 2. So if I take 2, then I reach the endpoint, that is 0. I reach the endpoint, that is 0, right. So at a level before only I am able to reach my endpoint. That is the more efficient solution than this one, right, because here I require 3 coins, but here only in 2 coins I am able to reach it, right. So this is the efficient solution. Also, one more possibility is if I take 2 at the stage 1, right, instead of taking 1 as a denomination, if I take 2 and then I take 1, that is the another combination, right. The order changes, right, only the order changes, and the denominations and the frequency of the coin is same, right. So at this position also, in 2 coins I am able to reach the endpoint, right. So this is 3 coins, this is 2 coins, and this is 2 coins. So what are the minimum number of coins which is required? That is 2. 2 coins are required here in this case. So with the help of this tree structure, we are able to recall a recursive solution. We can see that there are many problems which are overlapping, right. This is a small example. This is a small example. If you see the bigger examples with more number of coins and the larger value of the sum, you can recall that there are many problems which will be overlapping, right. We are just reprocessing it again and again to get a final answer, right. So the point of deduction is that this is a dynamic programming problem with overlapping sub problem and with optimal substructure. Why? Because when we get the optimal solution of this part, then only we can derive the optimal solution of this part. After that we can derive the optimal solution for this bigger sub problem, right. So with the properties of optimal substructure and overlapping sub problems, we can see that this is a dynamic programming problem, and we have drawn some of the observation that what we can do is, firstly, if we want, we can take the coin and reduce it from the total. Otherwise, we will not take the coin and move further. This is what we can do, right? So we will make a recursive call. This is the recursive function that we have. We'll make a recursive call. Let us say the count of function, and we will deduce from total the denomination that we are currently on. That we are making an index, that is current index, which points to the current denomination, and then we'll deduce that from the total, right. And we'll make the index as the same, because many number of times you can deduce that from the total, as we have seen here that we can deduce 1 multiple times from the total, right. So this is one possibility. We will make the recursive call. Otherwise, what with 1, and we will not deduce anything from the total. So these are the 2 main possibilities. So this is the minimum of these. The minimum of these will give us the result, that is our final answer, right. Whatever the number of count that we get from this, the minimum of these will be the answer. And what are the base conditions that we will have? If the total that we are getting, the t that we are getting is 0, right, the sum is 0, then how many coins would be required? That is 0 number of coins, right. So we'll simply return 0. Otherwise, if we're exceeding the array or the coins array, that denomination array that we have is 0, or we have the current index on which we are pointing is exceeding that array, then we will return some maximum integer, because at last we'll have to get the minimum of the 2 recursive approaches, right. So we'll return some maximum thing, right. So this is what a typical recursive approach is like, right. So you can write down the solution for this. Let's have a conversation in the comment section as well. You can post a solution there. If you have any doubts, you can write it in the comment section. This is a typical recursive approach that we're looking onto. Now it's the time to optimize this approach and see what optimization we can get through dynamic programming into this solution, right. So let's see how we can solve it in the tabular manner for this particular problem. Okay guys, so now let us understand the iterative approach, right? We have seen the recursive approach and we are clear to the problem statement as well, right? So now let us see how we can reduce the time complexity of the solution that we have. So we have exponential time solution as of now in the recursive approach, right? Because we have overlapping subproblems there. Now let us see how we can store the results of each subproblems and utilize the result to calculate the optimal answer for the next subproblem. So let's understand this. So what I did was, let us say that I have t equals to 11 and the denominations that I have, as I have taken an example, is 1, 2 and 5, right? These are the total denominations that I have and the total that I need to form is 11. So what I did was I made an array which is of size 12, right? That is 11 plus 1. I made the array of that particular size. What this array denotes is that for the ith sum, what are the total number of minimum coins that we require, right? For the ith sum, the total minimum coins that we require. We have the denominations with us as well, right? So initially I filled the whole array with 12. I filled the whole array with 12. Why 12? Because what is the maximum number of coins that we can have? The minimum denomination is 1, right? We cannot have a denomination which is less than 1. The minimum denomination is 1, and what is the maximum number of coins that we have is total value of t divided by 1, that denotes t, right? After that, any value is maximum to us. We cannot have a coin with that particular value. So I need to assign maximum value to this, right? So what I did was I assigned t plus 1 value, that is 12. We cannot have 12 coins for a sum of a sum of 11, right? We cannot have 12 coins. So I need to fill some infinite value, so I filled t plus 1 value there at each of the position, and one value which we need to know, right, which will denote the value for the rest of the problems, is this one, right? So if we have a sum 0, then how many coins would we require, right? This is a pretty logical thing, right? We would only require 0 coins, right? Because of any denominations we can take, it would not form the sum 0. So at this position we have filled with 0. Now for each and every position we can calculate the coins, the minimum number of coins that we have. So how we will calculate it? We have seen the recursive approach, right? So for the dp of I, let me call this array as dp array, right? For the dp of I, the minimum number of coins will be, first of all, the coins which we have calculated at the dp at ith position, right? And the value which we have is I minus coins of j, right? This is the value that we have, I minus coins of j. That means from the ith sum I am removing the coins of j, means the jth value of the coin. The j denotes the indices of these coins that we have. I am removing one, removing that particular sum because I am taking that coin, right? And when I am taking that coin, I need to add 1 over here, 1 plus dp of I minus coins of j. So what this value will denote is the optimal solution for the sub problem where we have the value that is I minus coins of j. That means the remaining sum that we have. We have taken the coins of this sum for our answer, and the remaining sum that we have, we need to look for that optimal solution, and we'll add plus 1 for it because we are taking the 1 coin for that particular answer, right? So this is what it denotes. So let us try to see how we will form it, right? So for dp of 1, let us take that we want to find the optimal solution for the sum 1, right? dp of 1 will be the minimum of dp at 1. So what is the value of dp at 1? That is 12 now, right? And 1 plus dp of I minus coins of j. So what is the coins of j? Coins of j means the indices starting it from here, 0, 1, 2, right? So coins of j is 1, right? So I 1 minus 1, that is 0, 0. So what is the value of dp at 0? The dp at 0, the value is 0. So 1 plus 0 will be equal to 1, and the minimum of 12 and 1 comes out to be 1. So at this particular position, the answer that we have till now is 1, right? The answer we have till now is 1. Now can we move towards the dimension 2 as well? Can we move to the dimensions 2? So think logically, can we form a sum 1 with the denomination of a coin 2? Is it possible? No, right? The minimum sum we can form with the denomination 2 is 2. We cannot form the sum 1 with the denomination 2. So we need to make a check over here that when we apply this formula, only when if I, the sum that we are looking into, is greater than or equal to coins of j, right? Whenever this condition holds true, whenever the sum that we are looking on to is at least equal to or greater than the dimension which we are taking, then only we can apply this particular thing, otherwise it won't work, right? That is the one thing. So for 2 and 5 it won't work for 1. So right, so what is the optimal answer that we get for 1 is only 1, because with one coin of one dimension we can form the sum as 1, right? Now let us look at for the 2 as well, right? So for 2, what do we have? We have these coins, right? So first of all, let us take one coin, the coin with the dimension 1, right? So if we take the coin with dimension 1, then what is the value at dp of I? Dp at I is 12, right? And dp at I means 2 minus the coin's j value, that is 1, right? So minimum of 12 and dp of 1. What is the dp of 1? 1 plus, right? So what is the dp of 1? That is 1. So 1 plus dp of 1 plus 1 is 2, the minimum of 12 and 2 is 2. So the answer comes out to be 2 for the value for the value of coin 1, right? The answer comes out to be 2. So we require only 2 coins for making the sum as 2 and of coin dimension 1. Now can we take the dimension 2 as well for the consideration? Yes, we can take a dimension 2 as well, because the value of I is equal to the coins of j. So let's see. Now we have value 2 and 1 plus dp of 2 minus the coins j value, that is 2. So what is the value here? 1 plus dp at 0. So minimum of 2 comma 1 plus 0, that is 2 comma 1, which comes out to be 1, right? So this is the more minimum value than this, right? So the answer at this particular position will be also 1. So for making a sum 2, we require only a single coin of dimension 2. That's it, right? So this is how we're trying to develop. This is how we're trying to make it, right? So for each of these values, right, we can form the optimal result. And at last, what we will do, we need to calculate the minimum number of coins for the sum 11. So we'll return the value that will be calculated over here, right? We'll be returning the value that is calculated over here, right? So it will be like 3, right? It will be calculated like 3. So this is how we are trying to build up the iterative approach, right? We have seen the formula also in the recursive approach. From that particular formula, we are trying to store it in the array and use the previous result to calculate the answer for the next near about results, right? So this is how it works. Now let us look at the code of this particular problem. Okay guys, so now let us try to make the solution for it. So I have written some pre-code here, that is I am taking the number of coins that I have, the denominations, the total length of the denomination array, and the sum that I need to form, right? And for each of the denomination array, I am taking the value of it, right? So what is the value of the denomination that I have? So this is what I have written. Now let's try to construct the solution for it, right? So first of all, I'll make the DP array, right? What will be the size? That is sum plus 1. And for each value in this DP array, I'll make DP of I is equal to sum plus 1, because I need to have some greater value, right? We have already discussed this. Now, what is the thing that we know here in the DP solution is that the value at 0 will be 0, right? And now we need to pre-compute the values, okay? So for int I equals to 0, I less than equal to sum, I plus plus. For each sum, I need to consider all the possibilities of coin, right? So I'll make a jth loop inside for the length coins that we have, j plus plus. And now the condition is if coins of j is less than or equal to I, that means the sum, the present sum that we are looking into, if the dimension is less, then only what we will do, we'll make the formula, that is dp of I will be minimum of dp of I comma 1 plus dp of I minus coins of j, right? This is what we have seen. Now what will happen if we do not get any of the solution, if any of the currency or any of the denomination that we have is not making up the sum? Then in that particular case we need to return -1, right? So how we can judge that is if at that particular position, if that particular sum, if we are having the default value, that is sum plus 1, that means we have not found the solution, because this is not the possible solution that we are looking on to. It cannot be there, it cannot reach there, right? So what we will do is, if at dp of this particular sum that I am having, right, if at dp of this particular sum I am having is equal to sum plus 1, then what I'll return, I'll simply return minus 1. That means there is no possible solution. Otherwise, what I'll return this dp of sum. Right, so this is what more or less the code looks like. Let's try to run this for this particular solution. So what exactly are we requiring for the output? That is the same input that we gave in the examples as well. The answer should be 3 for this, right? So let's try to build it and run it. Okay, so this is minus coins of j, right? Okay, so it is not coins here, it is denominations, right? So we cannot change it, denominations over here, right? And here also, if you see, it is denominations, right? Somewhere else also. Okay, now let's try to build it. Okay, so we are getting the answer 3, right? So this is the solution. Let's try to run it for some other values. Let's try to make a sum which cannot be reached, right? Okay, so let's make it 10. Let's make it maybe 3 or 7. Total number of denominations is 2. 3 or let's say 9. 9 will be good, right? Because 3 and 7 will sum up to 10, right? Let's try to make it. Okay, we are getting minus 1 in this particular case, right? So this is what the solution for coin change problem looks like, right?